this is the video physics should be watching after you guys did the punching thing. So if you haven't done the punching thing yet and you haven't been punched twice in the hand, go back and watch the other video or go do that and think about why go do it and then think about why they felt different, okay? All right, so now let's go ahead and talk about why from not just a big idea perspective. Let's actually get down to the equation here in just a minute, okay? All right, so I'm going to go ahead and start. This is going to be a quick little derivation here. You're not responsible for the derivation with the distance learning, but I think it is nice. I'm not a huge fan of derivations except when they help you understand. They always help you understand where the equation came from, but when they add something to that, okay? And the reason I'm showing this derivation is to make it clear that this is something that you're already familiar with, and there is another way to think about it. We're just going to rearrange it to make it more convenient, okay? So I'm going to start with F equals ma, our good old force equals mass times acceleration. And I'm going to do a little bit of substitution here. I'm going to change the acceleration to delta v over delta t. Now, a lot of times I won't write the delta t. I'll just put t, but because of where we're ending up, we want to emphasize that's a change in time or a time interval, okay? So delta v over delta t. Clean this up a little bit here, okay? And that'll be our force, okay? And now I'm going to multiply both sides by delta t. Multiply both sides by delta t, and I'm going to rewrite. So I'm going to have F delta t equals m delta v. Okay, and every line that I'm writing here is something that you could use to help solve problems. You're going to have a couple problems tonight. So if you see a version of this equation you like better, go for it. Okay, so now I'm going to go ahead and I'm going to rewrite the right side a little bit. I'm going to take this to be m v final minus v initial, because delta means the change in something. The final value minus the initial value. I'm going to have my f delta t still over here. Now I'm going to distribute that m. So I'm going to have m v final minus m v initial. Just doing algebra. Okay, a little bit of substitution right here with delta v over delta t. Everything else so far is just algebra 1 stuff, just playing around with the equation here. F delta t. All right, and now mass times velocity shows up so much in physics that we give it its own name, okay? Just like mass times acceleration shows up so much in physics, we call it a force. Mass times velocity shows up so much in physics, we give it a name, and it's momentum. So another equation you need to know is that the momentum, I'll emphasize that it is a vector, that's a lowercase p. Why aren't we using m? M is being used for a bunch of other stuff. Lowercase m for masses, capital M typically for masses of planets, and for molar mass and things like that. So lowercase p, that's a lowercase p. Okay, so P equals m times v, okay? And as we look at this idea of mass times velocity showing up so much, we give it a name momentum. It is a vector. Whichever way the velocity points, that's the direction of momentum, okay? If I run that way, okay, my velocity is different than if I run the other way. And you can't see it, but I do have a wall a little bit closer that way. So if I'm running that way, I'm going to get a different result than if I run that way where there's a door I can continue to go through, okay? So the direction of the velocity affects the direction of the momentum, okay? So whatever direction this points, okay? And then, of course, you just multiply by the mass, which is a scalar. It's just the amount, right? Amount of something. It doesn't have a direction. So they just do have to have the same direction. So that pops up so much. We will give it a name, momentum. So now, knowing that mass times velocity is the momentum of an object, I will come down here and I'll write this as momentum final minus momentum initial, because there's mv final, the final momentum, minus mv initial, the initial momentum. Still have that f delta t over here on the left, okay? Now, I'm going to rewrite one last time. So momentum final minus momentum initial. Make this a little bit more visually appealing. There we go. Momentum final minus momentum initial. That's the change in momentum of the object. So delta p. This equation is often referred to by me and as students as fat ap, because the deltas look kind of like A's. Okay, the deltas kind of look like A's. But what is it really? It's the impulse momentum theorem. This thing on the left is called the impulse. The impulse equals the change in momentum. All right, so now there's one little additional thing I got to add on here, the way we're going to use this, okay? And this is just a restatement of F equals ma, which means it can be applied anytime you want. This equation always holds, okay? But we're going to use it in particular during collisions and during explosions or when we're throwing something or catching something. And we're going to talk about the average force. So this is going to represent the average force exerted over some time will equal the change in momentum. Okay? All right. Now, go ahead and section that off. Let's go ahead and talk about the punching. Okay? So in the case where you were relaxed, let me take a step back. In both cases, you were supposed to receive the same punch. So how fast this is coming in is the same in both cases. Let's talk about the change in momentum of this fist, okay? So if I'm moving fast and I come to a stop, in both cases, I'm going to have a change in momentum, a rather large change in momentum for your fist, okay? So it'll be some big negative change in momentum if we're assuming the direction it's going is positive, okay? So negative however many kilograms times a meter per second. Oh, I should mention units as well. Kilograms times a meter per second. That's your units. kg times m over s. It does not have any abbreviations, okay? All right. That's one way to write the units for momentum. I'll give you another here in a minute, okay? All right. So for our change of momentum there, in both cases, the fist is going to come to a stop. So there is a change of momentum because it's moving and it's got a mass, and then it's not moving. So both of these, where we were like this and where we were relaxed, we will have the same change in momentum. This number will be the same for both cases where we got punched, okay? For the fist that's coming in. We'll talk about your hand in a minute. So what's the difference? The difference is the time. The one where you are relaxed will have the bigger time. So algebraically, if this number stays the same, okay, it's like we have xy, put this over here. It's like we have xy equals 8, okay? If I say y is bigger for something, that means x has to be smaller, all right? Let me add something there. Like if I had 4 times 2 equals 8, this comes up, depends on people's algebra skills. Okay, 4 times 2 equals 8, and then I'm going to make this value go up. Let's make it go up to 8. Okay, so this y value goes up, the x value has to go down. It would have to be 1 to keep this at 8. So there's a quick little reminder of that. Okay, so here with our, I'll leave that there for just a sec. All right, obviously you can open up my OneNote as well at home. All right, so if this number is staying the same like our 8, and one of them has a bigger time, the relaxed one, for this fist to come to a stop, the bigger time will have the smaller average force. And now we can connect back to good old Newton's third law, the whole you push on the wall pushes back on you. Well, if the force on this fist is smaller, right, if the force of the hand on the fist is smaller, so is the force of the fist on the hand, because they have to be the same size. So if you decrease the force acting on the fist, you also decrease the force acting on the hand, which means it hurts less, okay? So you want to increase the time of the collision to decrease the average force, because in both cases, the change in momentum will be the same. This is going to come to a stop, okay? All right, there's lots and lots of applications for this, okay? Eventually, we will talk about seatbelts, but I do want to mention one, don't get in a fight, okay? But if you do get in a fight, you may have heard the expression, either figuratively or literally, that you should roll with the punches, okay? The idea here for the literally roll with the punches is if you get punched in the face, okay? Obviously, someone says, someone's about to punch your face, what do? Duck, run away, yes, okay? But let's assume you're in a boxing match or whatever, and you're about to get hit, okay? You don't want to lock up your muscles here, because if you get punched in the face and you're really tense, you're gonna have a broken jaw and a bunch of teeth floating around in your mouth, okay? Now that might still happen, but if you're relaxed, and it's tough to have the presence of mind to get relaxed, you're about to get punched in the face. But if you can train and learn to relax, when you feel that contact, just let your chin go, okay? Relax all of these muscles, and it's gonna hurt a lot less because you've increased the time of the collision, decreasing the average force, assuming your change of momentum is the same, which we can for the fist coming in, okay? You're gonna get hit no matter what. You might as well increase the time over which that fist comes to a stop. All right, so that is your derivation. So whenever you are doing your two problems, okay, there's going to be some additional ones that are just about the basic idea of momentum. When you're doing your two problems based on this impulse momentum theorem, okay, you can use any one of these lines that you want, okay? So whichever one is the easiest to substitute into, go ahead and do that. Also for units, I should mention that this has units of kilograms times a meter per second, which is the same thing as a Newton times a second. So I could have a Newton times a second as well for my units. Okay, why does that work out? Okay, well, what does this equal? Kilogram times a meter per second squared, because that's just force, or sorry, times a, second. There we go. All right, Newton times a second, that's just a force, which is mass times acceleration times a time. One of the seconds will cancel out. They are equivalent. Kilogram times a meter per second, same thing as kilogram times a meter per second. So those units, either one is fine when you're putting your units on your work. Why are we doing all this instead of our typical summation of forces equals mass times acceleration or our motion equations and all that? It's because collisions are a mess, okay? So when you have, imagine a car crashing into another car, or you have a fist punching you like this, the directions are changing, the magnitudes of the forces are changing. So this is another tool in our toolbox that allows us to quickly get an idea of what's going on without having to do some giant computer simulation, okay? So when we're talking about during collisions and we use this is a heck of a lot better than the alternative because of the constantly changing free body diagram and it's a mess, okay? Think about a car crashing into a car, forces in all sorts of different directions. It's a big mess. We will also use this equation to set up when we can apply something called conservation momentum in a day or two. That's it. Have a good day, everybody.